Good morning everyone and hope you are doing well. In this video, we are going to look at the topics of the next topic, that is gravitation. And the topics that we are going to look into are Newton's laws of gravitation, variation of g, that is acceleration due to gravity with height, variation of g with depth, effect of rotation on g, and latitude effect. Now let's start with Newton's laws of gravitation, or in fact Newton's law of gravitation. Now what does Newton's law of gravitation say? Newton's law of gravitation says that if two masses are separated by a distance r, then the force between them is directly proportional to the product of the masses and inversely proportional to square of the separation between them. So that is what. So if I have to write it in terms of F, I can say F is proportional to m1 m2. F is proportional to 1 by r square, which gives me F is proportional to m1 m2 by r square. And the constant of proportionality g is called universal gravitational constant. You can see that this g is called universal gravitational constant. And these forces act along the line joining the two masses. Some important things that we have to see is magnitude of F1 will be equal to magnitude of F2 and they would be opposite in direction, so they can be forming as action-reaction pairs. Now this G is universal gravitation constant. That means it does not depend on anything else. So that is why gravitational force between two masses does not depend on anything else. That is, it's not affected by the medium between them. It's not affected by the presence of another mass between them. So, whatever is, if there are any changes apart from the changes in magnitude of masses and separation, the gravitational force between the two masses would remain same. And the value of G is 6.67 into 10 power minus 11 Newton meter square per kilogram square. This is what is value of universal gravitation constant. Fine. And the next thing, like if the masses are not point masses, then the distance between them is the distance between the center of masses. If they are point masses, so we don't have to bother about the point where the mass is concentrated. Now after that we have acceleration due to gravity. And how does acceleration due to gravity vary with height? Acceleration due to gravity is the acceleration with which an object which is close to the surface of Earth falls towards Earth. So if I have this as Earth, let's say an object is placed here, then the force with which object is being attracted by Earth, I'll write it as, we know that gravitational force is G me into m by, I'll say, r plus h whole square. This is the force with which it is being attracted. Newton's law of gravitation. This should be equal to m into acceleration with which it is coming down. We call it as g. Let's say g at a height h. Now this I'll take it as g naught. G naught is what? Acceleration due to gravity on surface of Earth, and on surface of Earth I can write g naught equal to g me by re square, where me is mass of Earth and re is radius of Earth. If I put all these things, g is constant, mass of Earth is constant, radius of Earth is constant, I end up with a value 9.81 meter per second square. So this is the approximate acceleration due to gravity at sea level or at mean sea level on the surface of Earth. Now let's come back to this. So gh is acceleration due to gravity at a height h. So I'll just cancel these things. So what would I get? I'll get g at a height h equal to g me by re plus h whole square. So this is what is acceleration due to gravity at a height h. Now let's get an expression for this in terms of acceleration due to gravity on the surface. I can say g at a h equal to, I'll write it as g me by re square. I'll take it out. I'll be left with 1 plus h by re whole square. So this can be further written as g me by re square is acceleration due to gravity on the surface of Earth. If I take it to the numerator, I'll get 1 plus h by re power minus 2. Now let's say h is very small compared to radius of Earth, maybe a few hundred meters, or if h is a few hundred meters or 100 meters or less than that, I can consider this to be very small compared to radius of Earth. In that case, I can write 1 plus h by re power minus 2. I'll just take the first term of binomial expansion. This would be equal to 1 minus 2h by re. So that would imply g at a height h equal to g naught into 1 minus 2h by re. Now again, this one is strictly applicable when h is very much less than radius of Earth. So remember that, so don't try to use it everywhere. When it is given that height is very small, then only use it, right? So because one common question that we have seen coming in exams is find the height at which acceleration due to gravity is 0. So if I apply this formula, I'll get h equal to how much? Re by 2. Now if I put this as 0, I'll get 1 minus 2h by re square equal to 0. So in that case, I'll get h equal to, so it's not re square, it is re by 2. But that's wrong because I cannot use it for heights which are comparable to radius of Earth. Fine. So very important point. This is possible only for, this expression is only true when h is very much smaller than radius of Earth. Otherwise, we can generally use this expression. This is always valid. Now let's move on to acceleration, variation of acceleration due to gravity with depth. Let's say I want to find what is acceleration due to gravity at a depth d. So when at a depth d, only this mass would come into picture, the shaded portion, because I want to find acceleration due to gravity, let's say at point B. In that case, I want to find what is mass. I'll assume that this mass is m dash. Assuming that density of Earth is constant, I can write m dash equal to total mass by total volume into volume of the shaded region. So I can get rid of 4 by 3 pi, 4 by 3 pi. So I get m dash equal to m into r minus d whole cube by r cube. So acceleration due to gravity can be written as g m dash by r minus d whole square. So I'll say at a depth d. So g at a depth d can be written as g m dash is m into r minus d whole cube by r cube into r minus d whole square. So instead of m dash, I have taken m into r minus d whole cube by r cube. So I'll just get rid of this. Then I'll be left with g at depth d equal to gm into r minus d by r cube. This is what we are left with. So if I want to compare with acceleration due to gravity on surface of Earth, I'll write it as gm by r square into r minus d by r. So gm by r square is acceleration due to gravity on surface of Earth. So this can be written as g naught into 1 minus d by r. So this is acceleration due to gravity at a depth d from the surface of Earth. So this is how I got it. Now I can see that, either I go away from the surface of Earth or towards the inner layers of the surface of Earth, acceleration due to gravity decreases. Now if I take this distance as x, let's say I take this distance as x, then instead of r minus d, I can write x. So if the distance from the center is taken as x, then I can say g at a distance x would be equal to g mx by r cube, or g is directly proportional to x. This is under what condition? When x is less than r. So this is how acceleration due to gravity varies with depth, and this expression is valid for every value because we have not taken any approximation. Only assumption that we have made is what? That that density of Earth is more or less constant. After that, let's move on to effect of rotation on G. What would be effect of rotation due to Earth? Now because Earth is rotating, there would be a centrifugal force which is trying to pull it away. Now what is centrifugal force given by? It is given by mv square by r or mr omega square. I'll talk in terms of equator. So if I take a look at the weight on the equator, mg naught would be acting towards the center and mr omega square would be acting away from the center. So the net force towards the center of Earth would be mg naught minus mr omega square. So if I take g to be the effective acceleration due to gravity, I can write mg equal to g naught m into g naught minus r omega square. I cancel this. So I can say acceleration due to effective acceleration due to gravity on equator is g naught minus r omega square. So we can see that acceleration due to gravity is slightly less than the actual acceleration due to gravity due to rotation of Earth. Now, we have questions like what should be the angular velocity of Earth so that an object on surface of Earth feels weightless. So So if it is feeling weightless, G should be equal to 0. If G is 0, I'll have G naught minus R omega square equal to 0, or G naught equal to R omega square. That would give me omega square equal to G naught by R, or omega equal to root of G naught by R. So if I solve it, you can put this as 10 and all those things, you'll get some values, and from that we can even find what is the time period of rotation at which an object on surface of Earth becomes weightless. So you can take G naught equal to 10. So omega equal to, I'll write Z naught as 10 meter per second square. R is 6,400 kilometers. So 6,400 into 10 cube. So this would be equal to 1 by 800 radians per second. This is what is angular velocity. If I want to find time period, I have 2 pi by t equal to 1 by 800, or t would be 2 pi into 800 seconds. So which is approximately equal to 1.4 hours. So we have questions based on time period also. That means if Earth rotates itself in 1.4 hours, then every object on equator would become weightless. That would mean that if you start jumping on equator, you will never come back. In fact, you can't jump, you can just take up once. You push away from Earth, you will never come back. So thank God it doesn't happen. I hope this is clear. The next thing that we have is latitude effect. That is, what would be effect of rotation at a latitude. You have seen effect of rotation on equator in the previous slide. So here let's see what would be effect of rotation at any other point. Now you can see in the figure that at this point I've taken at latitude phi, and I have found what are the centrifugal force acting on it. Mg will always act towards the center of Earth, and centrifugal force would act away from the circular path. You can see this is the circular path on which it is moving. So centrifugal force is acting away from it. If I find component of centrifugal force along the radius at point P, I see it is mr omega square cos phi, which is away from the center. So taking these two into consideration, the net force with which an object is pulled towards the center is mg equal to, I'll write mg naught. So here I'll write it as g naught minus mr omega square cos phi. Right. From this, what I can write? I can write g equal to g naught minus r omega square cos phi. Now what is r? R is the radius of this circular path in which object is moving. Let capital R be radius of Earth. Then I can say r equal to capital R cos phi by trigonometry. You can see that this is the adjacent side of triangle and r is the hypotenuse. Substituting that, what would I get? I'll get g equal to g naught minus r cos phi into omega square cos phi. So that will give me g equal to g naught minus r omega square cos square phi. This is the acceleration due to gravity at a latitude, I'll say phi, when Earth is rotating with angular velocity omega. Now from this, at equator phi is 0. So acceleration due to gravity would be equal to how much? I can write directly say at equator g phi equal to g naught minus r omega square. Right. Now at poles phi is 90 degrees. So phi equal to 90 degrees. Because phi is 90 degrees, then acceleration due to gravity would be equal to g naught. That means as we move from equator to pole, effective acceleration due to gravity would increase. So that means if your weight is something x units on equator, at poles it would be greater than x units. And again there is a catch here. It depends on the method in which you measure the weight. Like you are using a simple balance. Let's say you want to a 1 kilogram of potatoes you measure at equator using a simple balance. When you go to pole also, you will find that it is equal to 1 kilogram only, because whatever is the change in weight of potatoes is taking place, the same change in weight is taking place in case of the measuring bar that we are using to compare the weight of potatoes. However, if you use spring balance, then you will see that the effective weight of potatoes would be more at poles than equator. So hope you could follow this. Now let's have a quick review of what all things we have done. We have seen what is Newton's law of gravitation, that is gravitational force between two masses is directly proportional to the product of the masses and inversely proportional to the square of the separation between their centers, and it acts along the line joining them. Then we saw what is acceleration due to gravity. Acceleration due to gravity is the acceleration with which an object falls towards Earth, and we have seen how acceleration due to gravity varies with height and varies with depth, and we have also seen that acceleration due to gravity has maximum value on surface of Earth, and it decreases as we go away from the surface or go into towards the center, and acceleration due to gravity at the center is 0. And then we have seen effect of rotation. Because of rotation there is a centrifugal force, and hence there is a small decrease in the effective acceleration due to gravity, and this change vanishes as we go from equator to poles, because at poles the latitude is 90 degrees and effect of latitude becomes 0. Hope you could follow this. Thank you very much, and keep watching the other videos based on questions as well as the concepts of Get My Class. Thank you very much.